Hello. So in this lecture, we're going to start talking about convolutional neural networks, which are essentially neural networks that we use when we're dealing with image datasets. So imagine we are presented with an image classification problem where, for instance, we're asked to determine whether a particular image is a dog, a cat, a cow, a kinkajou, or whatever. But the idea is that we want to extract different features from these images that will help us determine what class they belong to. So we can already do that using the vanilla neural networks that we discussed in the previous lecture, but we're going to see why convolutional neural networks, abbreviated as CNNs, actually work better. So having said that, let's actually get started. So let's start with how we actually represent an image. So let's say we're given this image and its dimensions are 32 by 32, right? So for each pixel in this image, we have three values that are associated with it, right? So this is a color image, which means that let's say we pick a particular pixel, it's going to have an RGB value, right? So let's say an R of 0, a G of, let's say, 20, a B of 100, or whatever. But the idea is that each and every one of those pixels is going to have a corresponding RGB value for it. So when we're actually looking at this image, what we're actually seeing is a three-dimensional matrix of those following. So it will be 32 by 32 by 3, right? So 32 height, 32 width, and 3 depth. So that's essentially how this image is actually represented, right? So if you actually, let's say, load this image into a program, maybe using OpenCV or the Python imaging library, it doesn't matter, but the idea is that we could actually see it as such. Let's say we have, right? So maybe there's a value 0, 200, 1, 10, whatever, right? And so each and every one of those could be a different dimension, just representing the R, the G, and the B, right? Or whatever. So the dimension would be, let's say, 3 by 32 by 32, right? So this could be how we actually represent this image, and if you load it in Python or whatever other programming language you're using, you'll end up with a matrix like this. So this is essentially our data that's actually representing this image. And we want to create a classifier that distinguishes this image from other images. And the first thing that you can think of is, okay, if we're using a vanilla neural network, we could just unroll this entire matrix into one long vector and then feed that as our input to the neural network, and we'll be given the corresponding labels, of course, and then we can just train in that way, right? So that's one way you could actually train it. But we will see why there is a better way by using convolutional neural networks that would give us better performance due to how we actually go about doing it. So let's actually introduce the idea behind convolutional neural networks. So the first thing we need to talk about is the idea behind convolution, right? So what is convolution? So this is essentially described as a linear operation that we use for feature extraction, right? So let me just write that down. A linear operation for feature extraction. And the way that we would do that is essentially we compute an element-wise product between something known as a kernel and an input tensor. And an input tensor here is just referring to an image, right? So let me actually show you how the process of convolution works. And once you have an idea of how it works, then it will actually help us understand how convolutional neural networks work much better. So let's say we're given an image, right? And it's represented by the following matrix, let's say. So let's say we have, we have 1, 2, we have 0, we have 1, we have 0, let's say 1, 1, 1, right? Here I'm just picking some values that could be representing some kind of image, right? And so on, right? So there are going to be many values that are associated here with this image. So I'm not going to show all of them. I'm just going to show, like, let's say a part of them, right? So how does convolution work? So we define something that is known as a kernel, right? So let's say this is our original, this is our image, right? Because an image is going to be represented by these different numbers. So of course, here I just said, when we're actually looking at an image, there are actually 3 dimensions. If it's a color image, if we're looking at a grayscale image, it would just be 1 dimension, of course. And we're gonna look at all those things later on. But right now, just imagine we're just looking at it from 1 dimension, right? Because the same logic will expand to when we actually increase the depth, right? So, okay, we're given this image, then we define something known as a kernel, right? So we define, let me use a different color for this. So we have a kernel. So let's say our kernel is like 1, 0, 0, 0, 1, 0, say 0, 1, 0, something like this, right? So this is essentially our kernel. So how does convolution work? So we have an image, let's say this is 32 by 32, like we said, we didn't just show all the values. And then we have this kernel that is, say, 3 by 3. So the convolution operator, what it does is it takes, let's say, this part of the image, right? So this is a 3 by 3 part of the image, right? That corresponds, we apply our kernel on this part of the image, and we do an element-wise product. So that means that we take this 1 times 1, and we get, say, 1, plus 0 times 2, and we get 0, 0 times 0, which is plus 0, and then again this is plus 0, and then 1 times 1, plus 1, and then that's plus, this is 0, this is also 0, and then 1 times 2, this is plus 2, right? And we add all of this up, and this equals 4, right? And then, so this is essentially the operation, this is the convolution operation. We're just multiplying whatever this kernel is, and I'm going to explain what it actually does later on, but we're multiplying this kernel by this section of the image. And then, so this actually outputs something. So essentially we're creating another image, which is a multiplication of the original image and the kernel, right? So for this part, after applying this kernel, we get 4, as we saw here, right? So next thing we do is we move this kernel, right? We move it here, where I have got green again, right? We move it here, and we do the same computation. We say 1 times 2, and that's going to give us 2, plus, and then everything else is 0. 1 times 1 here is there's another plus 1, plus, and then here 1 times 0 is also, this is 0, and everywhere else is going to be 0. So this is 3. So what we do is we put 3 here, right? And then again, we shift it once more. We shift this kernel. Let's just use this color to the next point, right? We continually do this, and we continually try to fill in all these values. So as soon as we're done moving it from left to right, we start moving it from top to bottom, right? So when we're done with left to right, then the next time this kernel comes in this section, and so on, right? So that's the idea of convolution. So by doing this, we create this new image that we call a feature map. Okay, so these are the terms that you need to familiarize yourself with. So we have the original image, we have the kernel, which we call a feature extractor, and then after applying that kernel to this image using this operation known as convolution, right? This is the convolution. The convolution is just the multiplication, element-wise multiplication of the kernel with parts of the image, right? So you can think of this as, okay, we apply a kernel to the image and we get a feature map. So our kernel is essentially, our kernel is essentially acting as a feature extractor, right? So here we just chose some value for the kernel, but like we're gonna see later on that when we're using convolutional neural networks, we will try to actually learn those values. But the idea is that, okay, we have this kernel, it's extracting features for us from the image, right? And essentially using those features, we're going to try to determine what the object we're looking at is, right? Okay, so the kernel acts as a feature extractor, and different kernels can be considered to be different feature extractors because we're not just going to use one kernel, we're actually going to use multiple of them. So I'm going to actually show you an example here, right? So there are actually different kernels that do different things. For instance, if you look at this kernel that I'm showing you here, right, this is an identity kernel, which means if you apply it, you'll just get the same image that you actually had. This is a different kernel that if you apply it, it will actually tell you like where it will give you an image showing like, or a feature map showing where the edges are in the image. And you can imagine that extracting things like the edges of an image and so on, that's actually very important in actually determining what the image actually is, right? Because the structure that you would get for the kinkajou here might be actually different than what you would get if you're looking at, let's say, a car or a house or whatever, right? So these different kernels, right, extract different kind of features. This one sharpens an image, this one blurs an image, and so on. So what we are seeing here is the result of applying like different hand-designed kernels for different purposes. So in classical computer vision, essentially we would do something like this and use this information to help us determine, for instance, what that image actually is, or any other computer vision task that we're actually trying to do with this. But now with neural networks, right, we'll be given an image like this, right? We'll be given an image and we'll be given the corresponding label, right? So we'll be given multiple versions of this image and multiple versions of other images. And now we're trying to determine like what's actually important when you're classifying these images, right? So we saw that different kernels here have different values depending on what they're trying to extract, right? And it's hard for us to actually hand design like our own kernels. So we leave it to the network to actually learn which kernels it should use in trying to determine whether, like, what features it should extract from the image, what features are actually important in determining what class that image belongs to, right? That's what we use convolutional neural networks for, and that's the idea behind this. So let me just explain a few more things here, right? So we talked about, again, the original image, we apply convolution, right, by using a certain kernel, and we'll apply many different kinds of kernels. The values of these kernels are going to be learned by the model, right? They're sort of like our weights in a way. And from this, we'll build our feature map, right? So the other thing we need to talk about is, okay, so these are terms that are going to be important when you're actually implementing a convolutional neural network. And the next thing is something known as a stride, right? So this is essentially the distance between kernel positions, right? So essentially what this means is, okay, for instance, here I showed you an example whereby we start with the red, let's say the red kernel we're looking at here. So if we move from the red position to the green position, that's a stride of 1. We just moved our kernel by 1 step. So the stride is 1. But imagine we move from the red step straight to the orange box here. That's a stride of 2, right? So that's what the stride means. So as you can imagine, like if you have a stride of 1, like you more or less will have an image of the same size. Of course, you might need to add extra padding to actually enable that, and we'll talk about that in a moment. But the idea is that if you have a stride of 2, it's something known as strided convolution, which means you're actually downsampling, right? Because if you're having a stride of 2, you're actually missing some of the data that you have here, right? So there's actually parameters, these are actually hyperparameters that we can decide on. So like stride, which is the distance between kernel positions, and the kernel size, here I just put 3 by 3, but this kernel size can be 5 by 5, it can be 7 by 7, it can be whatever, right? The idea is that this is also a hyperparameter, whereby there are advantages and disadvantages of having a larger or smaller kernel size depending on what kind of problem you're solving, right? So having said that, the next thing we need to actually realize is the idea of weight sharing, right? Because if you think about it, we are taking this kernel, the same kernel, and we are applying it to all these different parts of our images, right? So we are scanning that kernel across all the image, and there are certain advantages in doing that, right? So this actually leads to weight sharing, right? Because we're sharing we're using the same kernel. We're going to learn the values of the kernel, which essentially are our weight values, and apply them to the different parts of the images. And the advantages of doing that are, first of all, there are less parameters to optimize, right? There are less parameters to optimize. That's the first advantage. And the second advantage is that there is also the idea of translation invariance, because we are extracting the features locally, so we can detect them no matter where they are in the image. That's the idea. So imagine this. So let's say we're given an image like this. So this is our image, right? And let's say we have an object here, and then same image, but the object is somewhere else, right? So these look like two different images in a way. And if it's not always obvious that if we actually use traditional vanilla neural networks, that would actually be able to detect that this is actually the same image or the same object in this image, right? It might actually be harder to do that. But since we're determining this by using, let's say, a kernel here, right? Here I'm just making it encompass the whole object. It could encompass part of it, but that's not the point here. The point is that the features that are extracted here by this kernel, right? The features we extract, the feature maps we get from this by applying the kernel here, right? And the ones that we would get from applying the kernel here, right? They'll let us understand that, okay, even if there is a shift in the object position in a different image, we'll still be able to determine what that object is, right? Because we are only looking at our features in a very limited, in a very local region. We're not using the entire image to determine what it is, right? So this is the advantage of using convolutional neural networks as opposed to, let's say, vanilla neural networks when we're doing image classification tasks. That's one thing we can think about here, okay? So having said that, the next thing we're going to talk about, so let me actually do that. Let me write that down here. So we're going to talk about pooling, right? So the idea behind pooling, or the pooling layer rather, is that it's a downsampling operation that we use to reduce the size of our feature maps and so on. So for instance, let's say we're given something like this. So we have 3, 2, 4, 2, say 4, 1, 4. I'm just writing some random numbers, just representing, let's say, an image or a feature map. It doesn't matter. It could be a feature map after convolution. But the idea is we have something like this. Okay. Now, given this, The first thing is, okay, let's first talk about something known as max pooling. And the idea behind max pooling is that we take a certain region of the image, say this part, and then we take the maximum value, right? So here the maximum value is 4, and then we move on to the next part of the image. The maximum value is 8 here, and we'll move on to this part. The maximum value is 7. Move on to this part, and the maximum value is 9, right? So we went from an 4x4 image to a 2x2 image, right? So this is a sign of downsampling, right? So that means we've done some downsampling here, right? And this also helps, again, with the idea of translational invariance to some extent. And it's also extracting the sharpest features in the image as well when we do this. So we also, it helps us in that regard, and it helps us reduce the parameters that we're using when we're actually trying to like create our convolutional neural network, right? So that's the idea behind pooling, right? So sometimes we might want to use max pooling to downsample. Sometimes we want to use strided convolution, which I discussed as using a stride greater than 1, right? Because that also downsamples. So if we have too large, if our images are too large, maybe we want to use these operations to help us like reduce our parameter size and so on. So that's actually the advantage here. So, okay. We've discussed the idea behind pooling. We've discussed the idea behind convolutions. We've discussed the idea behind the advantages and the disadvantages. Let's actually look at how it would look like when we're trying to like code it. So again, we're given an input, right? We apply our convolutional layers, we have our pooling layers, and then we feed all this to our fully connected layers. These are essentially the same neurons that we had before when we were designing a neural network, right? So the rest of it is just what we already know about neural networks. So the only difference here is that, so before, if we were just using neural networks, we would just feed our entire image as one large vector and create a neural network and an output. But here we're using these convolution operations and the pooling operations and so on to extract our features from the image because they do a better job than just using fully connected layers. Right, so this is how it actually looks in Pytorch. So the difference from what we looked at before is actually quite small. Like it's not actually very difficult. So if you look at this, when we're actually creating our layers, right, we create what's known as a convolutional layer and a pooling layer, right? And then finally, this is our fully connected layers. In this neural network, we essentially have 10 image classes, right? We have 10 image classes, and we're given a bunch of data sets of those images, and we're trying to train a model using this neural network, right? So we saw in the last lecture how to build a simple neural network, but here, when we're doing convolutional neural networks, there are a few differences. Okay, so let's actually describe some of these operations. So the first variable we look at here is called in channels, which just means input channels. So this is 3, right? Because, okay, when we're dealing with our image, we essentially have, as we saw here, so let me actually describe this a bit better. So this is our height, this is our width, and this is our depth, which is essentially our number of channels, right? Like RGB, right? That's what essentially this means. So having said that, that's what the input channels here is representing. And then the output channels is essentially like how many kernels we're actually going to have when we're actually doing our convolutional operation. And then the kernel size is the size of the kernel. Is it 3 by 3? Is it 5 by 5? Right? And then the stride here is 1. Okay? And then this is a maximum pooling operation, which means that we're just creating the same way we did here, a maximum pool of 2 by 2, right? And we just apply it on our image. And that's essentially what we have here. And then this takes, okay, the output channels of the previous layer are now the input channels of a new convolutional layer. And then we create, however, whatever number of output channels we want to create. So the more of these channels we create, the more feature extractors or kernels we actually have. And so these are essentially hyperparameters that we can use because we actually determine this by ourselves, as opposed to the actual like weights we're trying to learn here, which are actually the parameters of the network, right? And then, so this is how simple it is. You just create a convolutional layer with this, a pooling layer with this, another convolutional layer if you want. You can create as many convolutional layers and as many pooling layers as you want. But now the trick here is when you're actually feeding this to your final layer, right? Your fully connected layer, you have to do it in a certain way, right? Because you're gonna say, okay, I want to take all the parameters from the final convolutional layers. I wanna put them directly in my fully connected layer. And then here you can choose how many neurons you actually want. So you can imagine this as essentially having, let's say, some convolutional layers and so on, some pooling layers or whatever, right? And finally, we want to have this go into here, and then this go into another fully connected layer, let's say with 84 neurons. And then finally, it goes into a final layer that is like, let's say 10 neurons, right? That's essentially the structure of this network. So the question is, how do you compute this part, right? So the number of items that's actually going into the fully connected layer, there's certain formula that we can use to compute these feature maps, right? So let me actually tell you what this formula is, and we do it by saying W minus F plus 2P over S plus 1, right? Where W is our input size, right? F is essentially our kernel size, and P is our padding, and S is our stride. So first, let me explain the idea behind padding. So the idea behind padding is that if you are given an image with, let's say, values 1, 2, 5, 2, 5, 2, whatever, 1, 3, 7. Let's say this is our image. The idea behind padding is to essentially create like zeros around this image, right? You pad them with like essentially zeros or something like that. So that's the idea that we use behind padding and so on, right? So that we can recreate the original image size if we're just doing like straight convolutions with the length of 1 or whatever. So that's the idea behind padding, is just adding zeros around your image, right? So we are not using padding yet, so we don't have to worry about that. We're trying to make this computation, right? So first of all, we know that the output channel after convolutional layer 2, right? So the operation is this. Let me show you. So first, we feed our input to the first convolutional layer. We apply ReLU, which is essentially our activation function. We talked about that last lecture. And then after that, we apply it through a pooling layer, right? Then we take that to the second convolutional layer, apply a ReLU, and take that to our pooling layer, right? And then we take the output of that and we feed it to a fully connected layer, which is just our normal like neural network here. So we just need to calculate the input of this fully connected layer. So we know that we're going to have an output of 16. So there's 16 like kernels, right? 16 channels outputting here. And that's where the 16 is come from. But now I'm going to explain where the 5 by 5 is coming from. Okay. So our original image size, right, in this particular case was 32 by 32, right? So let's start with let's just start with any dimension with 32, right? So this formula is saying, okay, the input size is 32 minus the kernel size. Our kernel size here, we defined our kernel size as 5, right? We define our kernel size as 5 plus 2 times padding, which is 2 times 0, divided by a stride of 1 plus 1. So this gives us 27 plus 1, which is equal to 28, right? So that's the output after doing the first operation. So after doing the first convolutional operation, right, our output is 28, right? Here, it was 32, now it's now 28. So what do we do after that? So after doing the convolutional operation, we do a pooling operation. And we know our pooling operation, what it does is downsamples, right? And if we use a 2x2 pooling, we are just downsampling by 2, right? So here, our pooling size is 2x2, which means this is 28 over 2, which is equal to 14, right? So now our feature map size is 14, or more specifically 10 by 14 by 14, because that's the output here. So the input now is 14. So next, we do the next convolutional operation, right? So this was the output after, what? Conv1. After conv1, these are the dimensions. Then after pooling 1, these are the dimensions, is 14. And the next time we do again 14 minus 5, because we're doing again another convolutional operation, yeah? Right? And the kernel size is still 5, so that's fine. So using the same formula, it's 14 minus 5 plus 2 times 0 over 1 plus 1. And this gives us 10, right? So that's after convolutional operation 2, right? The size is 10. And then we divide that by 2 because we have another pooling operation here. And we get an output of 5, right? So we do it for this dimension and we do it for this dimension. Since they're both 32, they're going to just give us 5 by 5. And that's where the 5 by 5 here is coming from, right? So now you understand where the 16 is coming from. It's just the output channels, and 5 by 5 is after doing the convolutional and the pooling operations, like what is our resulting feature map size. And this is what they are. And we feed them to a fully connected layer. And then the rest of the code is essentially the same as what we did in the last lecture. You define your optimizer, right? You define your learning rate, and you just apply the gradient descent. So the rest of the code, you can just use the same that we used in the last lecture. And you'll be able to create essentially a neural network that is doing classification for this particular task. So as you see, the remainder is 120 by 84, 84 by 10, because there are 10 classes here that we're trying to classify, right? So that's essentially, in a nutshell, like what we do when we're trying to create this convolutional neural network. That's the modification to the code that we saw before, and the rest of it you can run it as the same. So here I'm not actually going to I'm not going to run anything now because I am actually going to prepare a bigger project that we can use convolutional neural networks in, and we can learn how powerful they are in actually determining what class a particular problem belongs to. So yeah, having said that, I'm actually going to stop here. So thank you for your time, and I will see you in the next lecture.